Okay. So ready? Oh, yeah, turn off your, and make sure you're muted. Make sure your laptop is muted. There we go. Now we're good. Excellent. Good deal.
Okay. Yes, now we're ready.
Yes.
Yeah, okay, so thank you very much for the kind invitation to come here. Yeah, so I'm going to talk about something that is not in the Einstein toolkit, but part of it is based on something in the Einstein toolkit. So I'm going to talk about Sphinx BSSN, which is a new code that I've been developing with my collaborator Stefan Rosbo from University of Hamburg. Where we do relativity with particle methods instead of standard Eulerian hydrodynamics. So this is the outline of the talk. So first I'll quickly give an overview of what it is, and then I will try to convince you that this is actually something that is probably a good idea to actually do. And then I will talk a little bit about the basics of smooth particle hydrodynamics. I must admit that Stefan is the big expert on that, so if I mess up, it's all my fault. Then I will just say a little bit about BSN. I don't think I need to say too much about it here, but I will highlight the things that are necessary to understand why the next step, namely that we need to couple the two methods together. And since the hydrodynamics live on particles and the space and BSN lives on the grid, we have to map things back and forth. Then I will go and show you a few test applications trying to convince you that this is actually working. And then I will show some results from, well, some movies and some results from astrophysical applications to this for finite neutron star mergers that has a front collapse and finite neutron star mergers with a long-lived remnant. And then some outlook and future developments needed. So what is Sphinx BSN? As I said, Sphinx BSN is a relativistic smooth particle hydrodynamics code that is coupled to a grid-based space-time evolution code. So this means that matter is represented by particles that move wherever the hydrodynamics and the gravity dictates them to go. And space-time is still represented on discrete points based on a fixed mesh. We actually implemented our own little fixed mesh refinement code here that then evolves to the full nonlinear Einstein equations. And it uses BSSN, as the name implies. So this is targeted towards astrophysical systems where the matter is warping the space-time significantly and thus cannot be treated in either the Newtonian limit or in a fixed background space-time. So, for example, neutron star, binary neutron star mergers, neutron star black hole binaries, and so on, or accretion disk around black hole and stuff like that. So, as I said, this is based on particle methods, so it's a Lagrangian code. So most other relativistic hydrodynamics codes are Eulerian, where quantities are attached to fixed grid points, and the change of quantity of at a fixed grid point is just given by the partial derivative data. And of course, here the one potential problem is that the resolution is determined only by where you actually put your grid. So if you don't have grid points, then if the matter moves somewhere else, you have to adapt to that. And that means that it's pretty hard to adapt to changing geometries. On the other hand, a Lagrangian approach, the quantities are attached to particles that move around with the fluid. And so you have to change your time derivative to be the full time derivative like that. And the one of the main advantages is that the resolution follows where the particle goes. So wherever you have a bunch of particles, you automatically have high resolution. And it's easy to adapt to changing geometries. Of course, that advantage gets diluted a bit when you actually couple it to a space-time grid, but at least that's one advantage of advancing fields.
Question.
Yep.
Does the trajectory of the particles, their accumulation at one point, give you a good idea where you want to refine?
Yes.
Okay.
It does. So it can actually help you in determining where you want to put your grid. Our grid is not that dynamic yet, but in principle you can. So another important thing to consider is another reason why we need another kind of relativistic hypertext code is just think of the case of a binary neutron star merger. And we know from the famous merger DW 170817 that where we for the first time actually had a multi-messenger event including gravitational waves. That's such binaries will produce both gravitational waves and electromagnetic counterparts. And so we know that the gravitational waves are produced by the bulk matter motion, whereas the electromagnetic radiation are produced by a small amount of matter that gets ejected from the main system. And this can be of the order of 1% of the matter. And one of the things that Eulerian codes have problems with is essentially based on the numerical methods used, high resolution capturing schemes, is that they have issues. Have issues with the surface of stars, and so typically you have to employ a sort of a low density artificial atmosphere around a neutron star. And this can also, the surface can also lead to unphysical outflows of low density materials. And when you have this atmosphere around, if you have some ejected material that moves away and gets to lower and lower density, eventually it will get to the level of the atmosphere, and then it just gets diluted and you can't really follow. And in order to really understand these multi-messenger events that hopefully we will see many more of in the coming years, it's very important to accurately describe this ejector that flows out in order to make a connection between the gravitational wave signals and the electromagnetic counterparts. And so, not to shame anybody, but this is just a plot I found in a paper, and any code, any Eulerian code could produce something similar to that, where you have a binary neutron star here, initial data, and then as soon as you start evolving it, because of this atmosphere and the problems at the neutron star surfaces, you start to see some material between the neutron stars. And much of that material will be sort of artificial and not really related to the physics going on. So this was, I just found this nice looking plot in a paper by David Battersby, John Whistle, and Galeazzi. But just to give you a flavor of what we can do with a Lagrangian code is, it's not exactly the same system, it's a different equation of state, but in our simulations of a similar system, and I made sure to make the scale, the logarithmic scale of the density the same. You see that as the neutron stars are moving around. There's no material between the stars at all. It's only when they actually get into contact where you start seeing a little bit of material gets ejected. The strange looking lobes here is mostly because of the visualization tool used and the fact that there's only a few particles. So there's a long large distance between them.
Yeah. Do you find it different without controlling the top by visualization?
Well, I mean, there will be a difference because they are different systems. It's not exactly the same system.
Depends on equal mass.
Well, they were both equal mass, but they were different masses, different equation of state. This was just to show that, or to compare the stuff between the neutron stars here.
It would be really nice to see something with the identical, parameters.
Yes. At some point, we'll get to that.
Okay.
But just to convince you that this strange looking lobes here, I can also plot the same where I don't actually color the things or the density, but just show the individual particles that we actually have. And you can probably see that there are some particles around here, but the density is quite low, but it all happens naturally. And also over here, you just see a few particles that have been started to be ejected from the central system. So as I also mentioned it earlier, advanced codes are good adapting to changing geometries. And so I'm going to show you a little movie here of a simulation that my collaborator made, not using full GR, but just Newtonian GR and just a couple of white dwarfs. Well, a white dwarf around a black hole where the white dwarf gets tidally disrupted, or partially tidally disrupted, actually. So there's actually a stellar core surviving. So let me just see. Oh, that's the wrong one. So you have the white dwarf coming in, getting tidally disrupted, but there's a core surviving here. You can see the scales are changing as the matter is moving in the background space-time there. And you can see that it sort of walks around the black hole again, and then simply this will intersect over here. And I think doing this with a Eulerian code would be pretty hard. You have to work hard to have the grids adapt to something like that. So let's just see that again.
I'm sorry, what was the physical startup again?
It's a white dwarf that gets tidally disrupted by a black hole. The black hole is at the origin.
Where's the white dwarf? That's the black hole, right?
No, that's the white dwarf.
Oh, that's the white dwarf. Where's the black hole?
The black hole is at 0.0.
Oh, okay, all right. This is black.
Well, 0. Yeah, so it's up here right now. And there's still the core of the white dwarf is still gravitational bound here. So, but as I said, once you actually couple this to full GR with a code with a space-time evolution, of course you lose some of these advantages. But I thought that this was a pretty nice.
Oh, so this is not a relative.
This is not relativity. The self-gravity of the white dwarf is Newtonian. So there's no grid here. You can just calculate the Newtonian potential based on the particle locations.
Okay, so you just do a sum.
Yeah. So in the past, there has been HPH code used in astrophysics, but they have typically been limited to, as in this case, Newtonian gravity or static background space-time or the quantum flat approximation to general relativity. And so as far as I know, this code we have been developing is the first that has done full GR with SPH. So what is the idea behind smooth particle hydrodynamics? The basic idea is that you replace the fluid by a finite set of particles. So instead of discretize your matter on a grid, you say, okay, let me just divide it into a finite set of particles. And we try to keep the particle masses to be about the same, so that's not too much of a discrepancy between them. And those particles are then allowed to move with the local fluid velocities. And in order to then calculate smooth quantities like the density, you can say, okay, I know where there's a particle there. So what is the density at a given particle? And of course, you have to do an average over a certain set of neighbors, and this is done with a smoothing kernel function with what we call a smoothing length h. So essentially, this picture shows here you give more weight to particles that are close to your particle, the particle you're interested in, and then eventually you don't actually see the remaining of the particles. So this smoothing kernel function then is used to recover sort of the smooth variables like density and so on, and also to calculate gradients. Yeah.
So like the edge, like the very outer particles, the kernel here to like change the kernel function.
No, you just use.
Repeat the question, please.
Yeah, so the question was what we do at the surface of the star, and nothing special happens there. You just use the number of particles that, of course, in this case, will just be on the inside of it. But there's nothing special to be done. And that is one of the reasons why we don't actually have any problems with the actual surface. So in some sense, the surface gets like smoothed out a bit because of the surface part having a finite smoothing length. But nothing special happens there. Yep.
A follow-up question. What do you want to do in SPH code if I'm interested in sharp features that are not necessarily changing the path? Trust or something. And you have to repeat the question.
Yes. So Roland was asking what we would do in SPH code if we were looking at something like a crust of a neutron star, and I must admit that I have no idea. I have no idea. We haven't talked about stuff like that yet. So, as I said, matter is described as particles with a mass m. So the A index here is labeling all our particles, and then the density is calculated as a weighted average over neighbors using this smoothing kernel function. So it depends on the distance between the two particles and the smoothing lengths that have been assigned to particle A. And so outside of the smooth lengths, the contribution is 0. When the distance is smaller than A, you get a contribution, and you get a larger contribution when the distance is smaller. And in the Newtonian limit, the equations can be derived from a Lagrangian. So essentially just the kinetic energy plus the internal energy. I'm ignoring here the gravitational potential. And from this Lagrangian, you can just do the normal thing and then come up with the evolution equations for the velocities and the internal energies. And they all have these kinds of, this forms here where you sum over a bunch of particles, neighboring particles, weighted with the kernel function, and it will also is grad A of the kernel functions will then give you the derivatives of the quantities you're interested in. So fairly simple stuff once you go through all the math. Many people think that SPH is very dissipative and very bad. And that is actually true if you just do the most naive implementation of it. It will be very dissipative. But my colleague or collaborator Stefan Vibho has studied this extensively and come up with various things to make things very accurate. So of course you can play around with your kernel choice, and some kernels have better properties than others. And for example, most people start out using something called standard cubic spline kernels, and these result in a lot of noise. They don't have too many neighbors, so when particles move in and out, you get jumps in your density averages. But if you use kernels that use more neighbors, can then reduce that noise significantly. But of course, since you have to sum over all your neighbors that are inside the smooth lengths of the kernel, you have to, this comes at a larger computational cost. And we do have to add some dissipation to the code in order to handle shocks. And those typically depends on differences in particle velocity. So if you have two particles coming together at high speeds, you are most likely encountering a shock, and you have to add some dissipation in order to handle that. But Stefan has also found ways of reducing the effect of that extra dissipation that you artificial dissipation have to have. For example, you can use, like people are doing in Eulerian dynamics, slope limiting reconstruction to the midpoint between particles to reduce the dissipation in smooth areas of flow. And you can also track entropy attenuation and steer your dissipation parameters so that they turn on when you have a lot of entropy generating, but not otherwise. And so with all those bells and whistles, it actually turns out that smooth particle dynamics can actually be made quite accurate. So just to show you here, we have a couple of kernels that we particularly like. The green one, or the purple one here is called the Ventland C6 kernel. And that was one that Stefan was using for a long time because it had very nice properties. One thing is that if you actually take the Fourier transform of that, the Fourier transform is positive as well. And that means that you avoid some instability, pairing instabilities that can otherwise happen. The green kernel is a higher order kernel that gives higher accuracy in your density estimates, but it's not, the Fourier transform is not positive, so it could potentially be suspect to some of these pairing instabilities that can be worrisome, but in practice we don't really see that.
I'm sorry, Q is the radius? Or?
Well, Q is the distance from between the two particles in units of the smooth lengths.
Okay.
So would be the RAB that I had in the previous slide. And so Stefan has been doing a lot of experiments and found that, for example, the VH kernel, the triple here, requires about 220 neighbors in order to give good density estimates. And so what we can do is we can dynamically adjust the smooth lengths of each particle, so it has exactly 220 particles in its neighborhood that are within the smooth length, and that's how we adjust the smooth length parameter as we go along. Yeah.
Repeat the question. What's the meaning of kernel?
Yes.
Well, so the kernel, I mean, is so the question is what is the kernel? And so the kernel is this mathematical function that has certain properties, namely that it should, if you, so these are what we call radial kernels, where the Q here is the radius between the radial distance between the 2 points you're looking at, and it should be if you take the integral of the kernel function over from over the region where the smooth length is non-zero, you should get 1, so that it's normalized. And then it should be something that has a maximum at the origin, and otherwise just goes to 0, so that you don't add contributions from particles further away. So essentially, it's just a function that gives more weight to particles that are close to you and less weight to particles that are far away, but with some nice mathematical properties. So what I showed you before for HDH was in the Newtonian limit, and in the relativistic limit, you can also write down a Lagrangian, which is a bit more complicated up here. And you have the splash energy tensor, the pole velocities, and square root of the determinant. But again, from that you can crank the usual methods of generating equations of motions and define the canonical momentum and canonical energy per unit mass by just taking derivatives of the Lagrangian with respect to your variables. And what you end up is equations that look exactly the same as the Newtonian case, except that these DIs here, where that used to be just the gradient of the kernel, now has terms involving the metric. And then you get these additional terms at the end of it that again depends on the metric, which are the essentially takes into account the gravity acceleration. And so we can define, like you do in Eulerian hydrodynamics, some evolved variables, and in this case, those are the, well, actually, first of all, you can measure or calculate the computing frame density from the location of your particles in your coordinate space, and then you can recover the rest frame density and so on from your evolved variables. And so we have, like you have in normal Eulerian hydrodynamics, we have to do a recovery of the primitive variables from the evolved. But that is all the same.
The subscript A there, like on GA, that is
the determinant of the metric at particle A.
particle A. Okay.
That's not a space-time index.
Right. No, I was just, I realized it couldn't be a space-time index. I was guessing it was probably the particle. Okay. But the I is a space-time index, right?
Yes.
Coordinate index.
Yes.
So the convention must be like ABC is particles.
Yes. And IJK is space-time or space indices here.
But we've also got mu and nu.
Yeah. So because those are actually four-dimensional sums over here.
Right.
Yeah. It might be a abuse of notation, but
Right. No, but it's just to be clear, there's 3 different types of indices.
Yes. So here I highlighted in red the places where the metric enters the SB equations. And so we do need to get the metric and its first space and time derivatives at the location of the particles in order to be able to calculate the right-hand size of the title variables. So now we come to BSN. So BSN we treat like any other code. We put it on a grid, and we use finite differencing. Well, not everybody does that, but it's not necessary to do that, but that's what we do. We use the standard 1+ log slicing and gamma fiber shifts that are known in everything else. But just to summarize the equations, in the BSN equations, you introduce the conformal metric, which is e to the -4 pi times the physical metric. And you do that so that the determinant of this one, the conformal metric is 1. And additionally, you do a trace decomposition of the extrinsic curvature, and a conformal rescaling of the traceless part as normal. And then you, of course, introduce the contracted Christoffel symbols, introduce as the evolve variables to make a standard piece. I'm sure we'll talk more about BSN during this workshop. So I thought I would keep this kind of short and just sort of show the equations here for all their glory. Well, not all their glory, because we'll have to write that out into specific indices eventually when you actually want to code it up. But what I just want to highlight here is, of course, that in the equation for the A tildes, you have matter terms. In the equation for the trace of K, you have matter terms. And in the equation for the contracted conformal, you also have matter terms here. So that means that in order to calculate the right-hand side for the space-time variables, you do need to know what the matter is doing at the grid points. And of course, we don't actually have the matter at the grid points at this point, but we'll get to that. So, as I said, matter information is available on the particles. Metric information is available only on the grid.
I'm sorry. Could you back up a couple of slides? One more. One more. So you have these S quantities that you evolve. Does this mean you did? Oh, wait, you had.
That's the canonical momentum.
Right. Those are the evolution equations. That means you don't have to have this Conda prim kind of thing that everybody else has.
No, we do because we.
Okay.
So
Are you still doing? Okay.
we still have the pressure here, and in what we measure is the.
Okay, but you still have that. That's
Yeah. We still have the step of where we have to recover the primitive from the evolve variables. So this is actually one of the points where we have to spend a lot of time in order to get things right and get things accurate. And so it has changed a lot from the first version of the code. So the mapping from particles to grids is the most complicated part, essentially because the particles are distributed non-uniformly. And so you have to figure out a way of getting quantities mapped accurately from a set of non-uniform points to whatever grid point you're interested in. And so the current scheme that we have uses what we call a local regression estimate in combination with something we call a multidimensional optimal order detection scheme. It's a mouthful. But the main idea is fairly simple. you have a grid point here, and you have a bunch of particles around it. And so what you can do is you can expand the quantity that you know at all the particle locations in a Taylor expansion around the grid point. And so you get the quantity is equal to the quantity at grid point plus the derivatives at grid point times the distance and so on. And then because you have more particles than unknowns, the unknowns here are the value at the grid point and the derivatives of the grid point.
10 minutes.
You can expand out and you can use, when you have more points, you can use linear regression to solve for these quantities to different polynomial orders depending on what you want. Then you can evaluate this function that you have on the grid points and measure the error based on the value that you know is existing there. And then and you can weight that by the distance to the grid point using one of these kernel functions. And then you can choose the order that has the smallest error estimate in order to get things as accurate. So that's the main idea. We calculate these at different orders, and then we look at the errors and then choose the one with the best error. Unfortunately, that doesn't quite work near the surface of the star. So we need another way of detecting the surface of the star. And we came up with this expression here. So if you take the divergence of the radius vector, you should get 3. And so if we calculate this using an SVA estimate near the surface or everywhere, you should get a value that is close to 3. So if we construct this quantity here, then that should be close to 0. And it is, if you actually measure that, most of the places except near the surface of the star. And this is exactly what we want. We wanted to get an estimate of where the surface of the star is. And so we can look at this, and then where this error estimate is above a certain point, we can go and say, okay, let's use the lowest order linear regression results for that point, because otherwise you might get a missed. The mapping of the metric and its derivative from the grid to the particles are simply done by fifth order pyramid interpolation. So standard, well, not quite standard, but almost standard polynomial interpolation. So here's the schematic of the algorithm for taking one time step. So first we have to convert from the SSN variables to physical metric. Then we have to map that physical metric from the grid to the particles. Then we have to update the neighbor tree that is used to calculate the to figure out which neighbors to include in your sums to get the smooth variables. And then you can then calculate the local rest frame density. Then you recover the physical height of variables from the more variables. Then you can calculate T mu and map that from the particles to the grid. Now you can calculate the time derivatives of the metric variables on the grid. And then you can map the metric acceleration terms from the grid to the particles. And then you can finally calculate the time derivatives of the hydro variables on the particles. And then you can figure out, okay, which of the is the hydro or the SN equation the most restrictive in terms of time step, and choose the one that has the smallest time step requirement. And then you can update the hydro and metric state vector based on this time. And then all the particles move, and then you just repeat. Yeah.
Through that, there's parts paper.
Yeah.
Do you have to update this?
Yes. The smoothing lengths, I think it's doing this update of the neighbor tree gets updated so that we have exactly the right number of particles in.
That's different for every.
And that will be done for every particle, yeah. So just to show you a test application, especially with a specific shock tube, you have a high density, high pressure matter in one side, low density, low pressure in the other side. This doesn't actually have any GR, but it's done with the full GR code with just the metric set to Minkowski. And you can see that the code
5 minutes.
is able to track the exact solution quite well. But it was just something that we needed to do in order to show that we can actually do shocks. Second application was just take a stable TOV star, put it on our put the metric on our grid and come up with a distribution of particles to represent the density and pressure structure of the star. Here we just use a polytropic equation state with gamma equals 2, this mass and so on, because that was something where I could compare something with in the known stuff in the literature. And so once you let it go, there's some oh, sorry. Thank you, Eric. There's some numerical error, of course, truncation error.
People online can't see where you're pointing.
Yeah, I know.
Okay.
But I can't do it
Yeah.
both places. And so you see that we've done evolutions here with 500K particles, 1 million and 2 million particles. The full space-time evolution here. You see that the oscillation amplitude of the oscillations decrease with resolution. And if you take a spectrum, then we see quite clear peaks at the expected frequencies of the eigenmodes of the star, fundamental mode, and up to, well, just see barely a trace of the fifth harmonic mode, but at least we see that. And what I also wanted to show that after evolving this Newton star for almost 30 milliseconds, it's a long time in this is the particle distribution. So you can see we still have a very well-defined particle distribution that doesn't do anything strange near the surface of the star. And we also see, so in the black, we show the initial density profile, the density as a function of radius. And at t equals 30, we see that it has hardly not changed at all. Of course, there's some oscillations, so it will, and some of the particles have moved away from the initial position. But again, everything is nice and stable, and no problems with the surface. And I should also mention that here I am showing all the particles, so there's no particles that are off or something. Yeah.
Repeat the question.
Yeah, so the question is if we see any quantum failure, and in this simulation, not. Once we have start collapsing to a black hole, if we don't actually increase the grid resolution, we will see it because things get unphysical. But as long as we keep the grid resolution compatible with the particle density, then we don't see anything. I should then go here and just give you a flavor of what the code can do by showing this movie here. So this is going to be a binary neutron star with two 1.5 solar mass stars with the APR3 piecewise polytropic equation of state. And you see, we just move around, move around, move around. And everything merges and the black hole forms, collapses. We start removing particles. And at the end, maybe a few thousand particles left, starting from like 2 million particles. And some of them actually gets ejected with a very small amount of matter here, but the code can handle it. But of course, in order to really get that accurately, we probably need to do simulations with more particles. Yeah. And then we can also do binary nucleus mergers with long-lived remnants. So if we just decrease the mass a little bit here, at least with this version of the code, we can actually have a stable, a long-lived stable remnant. So let me just go and show you that movie. And again, I point you to the fact that there's nothing going on between the stars. And then at some point, we start developing L=1 asymmetries that grow. Those are, I think, expected instabilities that makes things look like wobbly here. And in this case, eventually, the black hole actually, after a while, in this simulation, a black hole actually does form, but after like 15 milliseconds. Yep. And I found that it was useful for this case to actually look at the velocity as a function of radius. And so you can see there seems to be sort of two different phases of ejection of high velocity material happening. There's this first leading phase and then the second one. And there's a few more in here. And in this case, only about 7 times 10 to the minus 4 solar masses actually escape. But some of it actually escapes with velocities that are close to 80% of the speed of light. And I also made a movie with this. So initially we have the nuclear star just wobbling a bit, and then we have the first ejection, second ejection as the star oscillates and material comes in and hits that and then moves out again. Just pause it here. You see it's ejected accelerated to pretty high velocities here. And then have the same, the second contraction phase here. I found that pretty cool. And I should probably go to the last frame, no, last slide, and talk a little bit about the outlook and further developments. And one things that we need to get done is to do a distributed memory parallelization of the code, because currently it's only OpenMP parallel, and that limits to the number of particles we can actually go to, because the runs take quite a long time then. I would also like to add an actual apparent horizon finding to the code itself, so I don't have to read it into Cactus afterwards and use the apparent horizon finder direct there. We need support for more equational states. Currently, we have polytropic and piecewise polytropic, but Stefan is currently working on tabulated equational states, so we can do more interesting things. We would also like to have sort of an improved matching of the numerical method of escaping particles with a background space-time to continue evolution. Because we have a grid, we have a limited region that is covered by the grid, and when the particles get to the boundary of that, we want to just map them to a background space-time and then continue evolving them so that we can follow the outflow to for long times. We have done some work there, but we need to improve what we're doing. We also need neutrino transport because we, of course, need to know what happens with neutrinos. We need to know how the electron fraction of the escaping material in order to produce reliable light curves. And, there's probably a lot of other things we need to do, but this is what I have chosen for this. I'll stop here.
Yeah, well,
A lot of questions on the way.
we allowed you for 15 minutes for questions, so hopefully that's more than enough. Yes, Leeway.
Easy to add.
Is it easy to add magnetic fields?
Don't think, well, I don't know, actually. I know that I think Stefan has some ideas of how to do it, but I don't know how difficult it would be myself personally. But yeah, I mean, I think Stefan's priority is to get the tabulated equational state neutrinos done, so we can follow that kind of physics better before looking into magnetic fields. I don't have it here, but
Repeat the question.
so she was asking if we have an angular profile of the ejected material. I know that Stefan has looked at it, and I think he found that the first burst that we see that comes directly from the initial collision seems to be more in the equatorial plane. Whereas the second phase, where you actually get
5 minutes, please conclude.
of the hypermassive core is more isotropic, but it's something we need to look into more. That would definitely be interesting. Yeah, I suspect that they probably just have tracer particles that are moving with the local fluid speed, and I think that would also be affected by the atmosphere. But yeah, it could be interesting to look at.
For the folks. They just thought like.
Okay, so the question is, did the code crash when the black holes form? And the answer is no. As long as we add more refinement levels as the particles move in, then eventually they get far enough inside that it's safe to actually remove the particles. So at some point we do it actually in 2 stages, where we first convert the particles to dust once they get far enough in, so that they just keep going with geodesic motion. And then once they get even further in, then we finally start to remove them. And when we do that, we can actually evolve the black hole afterwards stably on our grid when there's only a trace set of particles flying around somewhere, or sometimes all the particles actually go into the black hole.
All right, I think I'm gonna stop the questions there so that Amrutaa has time to set up. And any other questions, Peter will be around at the break and we can interact.
And I will be here the rest of the week as well.
And he'll be here the rest of the week. His flight for the second floor doesn't leave before that. So let's thank him. There is power up here. Well, of course it does.
Yes,
The power,
Oh, it's here.
yes.
If you would like to use the.
If you want to use this this clicker thingy,
Oh.
Yes, you can make the screen go.
Okay.
You
And
can
the
move
power-
wherever you want to.
power's back here.
Yeah.
Right. Leave your spin.
Dr. Diener, when you get a chance, you can, I'll show you a screen for me.
Oh, yes. Sorry.
So when you share your screen, it's like he has it, if you want to, you can move around.
Okay.
And you can see the.
Right.
Exactly. It's got a green.
Dr. Haas, was it tinyurl.com ET 24 or what was the URL for this one?
Yeah, you can.
URL. That's
ETUS. Uh,
Maybe you want to mute your computer.
Yeah.
It's up.
okay.
Make sure your computer's muted. Okay, share your screen. You sharing your screen?
Yeah, I'm just gonna go into this one.
Oh, okay.
Okay.
And then for here. If you
Forward, backward.
forward backwards, if you accidentally press this, it just blocks it out, just press it again.
Got it. Thank you.
And then I share.
Thank you.
You're welcome.
All right. Can start like 1 minute early. Everybody should be here. Okay. So our next speaker is Amrutaa Vibho from Norwich University. Go ahead.
Thank you, Dr. Brandt. Can everyone hear me? Online?
Yes, should be able to.
So this is going to be very different from what the talks have been today. I am not by any means a PhD, a grad student, even a graduate of college. I'm just here because Dr. Brandt and Dr. Haas agreed to have me here and taught me a few things last year that I'm carrying forward this year. Good afternoon, everyone. My name is Amrutaa Vibho. I am a student of Norwich University, which is a military college in Vermont. One of my co-cadets is here. He's also from my university. How this works is we study during the day and train during the night, train in the morning, stuff like that. I'm going to be speaking about my very first research project that ended up getting published. And if you remember from Dr. Brandt's talk, there are some people that focus on machine learning applications in the field of fundamental relativity, cosmology, stuff like that. I'm one of those people. Dark matter subfield multiplications using machine learning focuses on applying dark matter, applying machine learning on the Fermi DAT catalog, which is released by NASA called Space Flight Center. Those are gamma ray observations with the Fermi DAT telescope, and I'm trying to see if we can map out possible dark matter correlations. How this is relevant to the Einstein toolkit, I will. A little bit about me. I'm from India. I am a student of physics and math, and I study chemistry and mechanical engineering at minor. This actually is a very recent photo of me down in Houston, mission control center, because I'm interviewing to be in the next class of astronauts. I don't know why I applied, just for fun. Let's see what happens. That's my chemistry research right there. This is research I do with the Vermont Space Ground Consortium on hyperspectral imagery of nanoparticles and using them to make a portable, essentially, water treatment system for the International Space Station. My main research that I want to do as a graduate student would be high energy astrophysics, which is why I'm here. That's the paper that ended up being published. So when I was graduating from high school, it was COVID year. Obviously, I actually got into UIUC, and I was supposed to go to UIUC for aerospace engineering. Then ended up being able to go with COVID. Started doing research with students from the University of Chicago through the Brandt academic research program. And they were teaching me applications of machine learning, and sort of left me on my own after that. So I found interesting topics and an uninteresting paper on an application of machine learning on the Fermi DAT catalog years before, which is what I started doing with that year's incremental catalog with Postma. The idea is that according to the lambda cold dark matter model, the matter energy equivalence, we are trying to model through n-body simulations, cold dark matter, dark energy, stuff like that. How interesting would it be to see if gamma rays are actually emitted from dark matter sources? Because we don't know what dark matter is. We don't have any equipment to say, we don't have what candidates they are. The idea behind it is, so we have, of course, positive confirmation that dark matter does exist, because the universe is expanding and there is more matter in the universe than is observed. In 1933, Fritz Zwicky, actually, as most of us know, released his paper on the redshift of extragalactic nebulae that we observe more matter than we can observe with electromagnetic. So that interacts optically. And so the Fermi DAT catalog records gamma ray sources from outside the Milky Way, nearly extragalactic and galactic sources. And most of them are associated sources, meaning their sources are known, as I have on the right side. But this particular research focuses on building a dark matter subhalo set using pulsar data, globular clusters, and associated clusters. So according to lambda CDM, there are theories that weakly interacting massive particle problems and massive compact kilo objects, macros, fall in the range of dark matter annihilation. So their flux falls in that range. 70 electron volts for this particular experiment from that catalog. So that gives us hope of trying to compare the energy spectrum of these sources with the unassociated sources using machine learning, learning complex patterns, and seeing if our model classifies these unassociated sources as possible dark matter. That's what I did. Why machine learning? Because it can uncover patterns that are not otherwise apparent. Can it have its faults? Yes. Which is where numerical relativity and what I'm going forward with. So I use multi-layer perceptron, which is a neural network, an artificial intelligence architecture, and support vector machines which are Bayesian, which is why I asked the question earlier on Bayesian hypothesis analysis. And the false positive, that's my false positive case. But as you can see, it's pretty decent for the most part. So on the Fermi DAT catalog's fourth increment, there were 5,788 sources that were associated with a known gamma ray source, 1,667 unassociated. That's a big number that's not good. So I basically chose the ones that are above 10 degrees of the galactic, or almost extragalactic. Out of those, I could classify 30 using my model as potential dark matter candidates that have the flux density within this dark matter annihilation range and the gamma rays correspond. This is the data projection. Challenges. It's a very big claim. Taking a catalog, using machine learning, claiming I know what dark matter is, or I found dark matter today. What I'm trying to do is, I could get the annihilation cross section of these candidates that I identified, but the process is more complicated than my undergraduate brain. What I can possibly do is use LIGO data. So between the fourth increment, which was my first research of the Fermi lab, the fifth one, which was released later in 2023, December 2023, some of the sources that my model positively identified were moved to laser stuff. That is not very good for my research. But my now advisor and I started looking in the direction of what if these are not self-annihilating dark matter structures. There are other theories that explore possibilities of dark matter being something else and not a part of the nature. That's what LIGO. Primordial black holes could possibly be dark matter is a stipulation, has been for a while, especially since LIGO's first observation. So last year, I embarked on this journey, Googled black hole, LIGO, machine learning. Dr. Haas has made me on. Dr. Haas and Dr. Eliu, who work at Argonne National Lab. He works at Argonne National Lab. They work at the gravity group, doing simulations of highly eccentric black holes. Emailed them saying, I'm an undergraduate student. I did this. I don't know what to do. He said, come to RIT. We have this conference. So I met Dr. Brandt and Dr. Haas last year and realized that I could use numerical relativity to simulate primordial black holes. Parameter estimate using a catalog of sorts that I would get, then try to apply it to my dark matter catalog and see if there is a difference or it's impact. Now, of course, that's more difficult than I can imagine or imagine. So this is the research that I'm going off of. Right now, I have a catalog using these parameters and hyperparameters that I generated using AstroPy and Python mostly. My first step is to try to use the Einstein toolkit to simulate some of the things that I got using Python, which is why I'm here today. And I've been trying to ask and take help from Dr. Haas and students at NCSA and RIT to do this. My next step was to try to study the companion. The lambda CDM, I did start on the CDM, I wanted to study lambda. This is my advisor, Dr. Brandt. We are trying to study the dark energy model using bulk viscosity as an explanation for dark. So his research believes that the negative pressure that is created by dark energy could also be contributed to by bulk viscosity, which they publish. And what he's looking at with me is the effect of shear viscosity that is possibly contributing to the perturbations of the particle. We use something called the Cosmic Linear Anisotropic Solving System. It's a C++ based code that solves for Einstein equations. And my job this year is try to implement a module, like you spoke about modularization. I'm trying to modularize, to take the part on shear viscosity, how it affects these graphs that we got from the previous research on bulk viscosity. If it matches up with what we have here. I don't expect to be able to answer a lot of your questions because I'm here because I'm excited about what I'm presenting, what I'm researching. Hopefully, you will have some input for me on what I could do in the future. This is all I have. Thank you for having me. Any inputs, any questions?
I don't understand exactly what you're trying to do, but I'm trying to understand, trying to correlate two things, dark matter and some phenomena.
Dark matter and primordial black holes, because we
You have to
don't-
repeat the question.
Sorry. Okay. So the question was, if I'm trying to correlate dark matter and something else, how I started off was trying to figure out if dark matter comes from gamma ray sources, mostly pulsar light, because they emit gamma rays, so and their gamma ray density, flux density falls within the dark matter annihilation range of 20 to 70 electrons. So when we started off with that, we found out that there is a good chance that the candidates we're looking at are not annihilating dark matter. So not gamma rays or pulsars. It could be primordial factors.
So what's this machine learning is for correlation study?
Sorry?
What's the difference between machine learning and just a correlation study?
The question was, what's the difference between machine learning and using correlation study? I would argue using machine learning, so there's something called transfer learning that I'm trying to use to transfer the effects of training my model on known sources to when I change the input to unknown sources. Now that would help me decipher between like I could transfer the same model between my gamma ray source catalog and my primordial black hole catalog. I would argue it is more transferable and more modular. I can add to it without modifying the code structure.
That's just correlation analysis.
I do see that. I guess correlation analysis because this is what I chose. But I wanted to go to.
Understand that.
Any other questions? So did you find any new blob that you could identify that no one has identified before?
There are four
Four.
in my paper which I do not have one with them. But those four, I don't have it right now, but on my paper in the future work section, I have included that those four fall in the X-ray catalog of Chandra X-ray also.
And they were determined to be black holes?
They were determined to be pulsars,
Pulsars.
but we don't know with confidence. So they were in the TS9 error region of the
Okay.
Chandra X-ray catalog. So they could possibly have X-ray counterparts, and that's what we're going to do. So
Okay.
I did.
All right, any other questions? Okay, I guess not. Thank you, speaker
Thank you.
again.
That's not great.
Correct.
You're the boss.
I'm the boss, but I obey the schedule. Let's see, what do I have?
Yeah, we're on break. And then we have tutorials.
We're on break until 3 o'clock, and then we will have our tutorial. For those of you who are interested, I should give you the code again. They're vampires too. Let me do the screen share. Let's see. All right, so if anybody wants to set up for the tutorial early, you can create your name and log in, use your login name and password using that code, Withered Vampire 2. No, and that's actually randomly generated. It could be a book title, Withered Vampire 2.
It was the third quote.
Don't make a one to start.
That's right.
That's to the.
It does. I agree. It does. Withered Vampire 2.
Senior students with romance novels.
Withered Vampire 2. It's totally random.
You won't.
Especially.
one of the few sitcoms I think sit through.
I don't know, I have trouble with it.
Oh, with yes.
Thanks, yeah.
I mean, so, with Brandt, it's the same version, like, Brandt probably. So, Brandt has a bit of primary. That bill, back.
Easy cable, oh, I'll put that up there soon.
Yeah. We do that. That's. Road. But it's set up from back. This.
Coming from the ground.
Except the fee is, the loss is different.
Yeah, I have to take that out.
Yeah. But
20 answers.
Yeah, you'll have to. Great.
I did that one with.
Yeah.
Not by setting up. By a little bit, the data, and then we look possibly this data set up, and then sets up some data. Yeah. But we also want that But then it kind of stop. So they found the diverse velocity and track with some pressing smack. That as well. Yeah. Sometimes when set up models, usually does we just that out. space. Everyone has not quite yet. It's still different. Quite enough.
An unknown character. Error. Right. Minimized on me. Share. All right. So. Let's see, how many people have we got online? Participants 9. We've got 9 participants online. And we've got more than 9 in the room. So somebody was kind enough to broadcast the code and the server name to everybody in the room. If you have not done so, please create your login. In order to do so, you can visit the URL that's given in the chat. And that withered vampires 2 goes into the code at the bottom, but you can invent your own login name and password. And once you've done that, you should get an account that's pre-populated with all the tutorial notebooks. In case you have already started experimenting with the notebooks, please note that right before this talk, I regenerated all the I recopied all the notebooks to your home directory. So they might have, if you had done something, it might have gotten overwritten or changed. And sorry about that. It's a one of many weird technical problems that I'm sure we'll face together. So while you're in the process of getting your login set up, if you have not already done so, is there anybody here who is unfamiliar with Jupyter Notebooks? Is there anybody online who is unfamiliar with Jupyter Notebooks? Speak up now or forever hold your peace. You know what? This is the first time I haven't gotten a bunch of hands at this point. Okay, so proceeding with your expertise, knowing you're experts in Jupyter Notebooks, let's take a look at what we've got. Now, most of the stuff in prerequisites isn't relevant to this particular session, but it will be relevant if you want to set up the Einstein Toolkit on your laptop directly. We don't want to set up the Einstein Toolkit on people's laptops directly as part of this tutorial because too many things can go wrong, and you know, it just depends on all the little details of how your laptop is set up, and it's something that we could potentially fight with for hours depending on what your laptop is like. On the tutorial server, we have a controlled environment. We know exactly what things are installed and where and so on. And so it's much easier. So these instructions are for you to look at home if you want to run directly on your laptop or cluster. Scrolling past them, we have this magic cell. And it's just got a couple of definitions that we like to use within the notebook itself. In particular, it has this %% bash thing that it sets up to work a certain way, and environment variables it sets and so on. The ET setup is just a place to standardize all those little settings. So just execute that cell. Now, the next thing to notice about the Einstein Toolkit, we're going to teach you how to download and install the full software package. And it is way too much, even for this tutorial server, if we were to have everybody in the room simultaneously download and install the thing. It would overload the network, right? If everybody's suddenly downloading all that data over the network. And it would cause other problems as well. So we have what's called an optimized build experience, where we have a pre-built cactus binary in the tar file. And by running this cell, what you're going to do is extract this. And it's going to make sure that you have all the files in all the correct locations with all the correct file permissions and modification times and so on, so that your build, so you won't have to rebuild hardly anything. And all the steps that follow will do mostly nothing, except they should work the same way with or without untarring this thing. They should give you the same result at the end, but it should just take far less time. So this step is going to take a little while, partly because we're now overloading the file system, right? Because everybody is doing this same thing, and it's overwriting everything. Now, if at any point during this tutorial you screw up your installation, you modify some file or you break something, you can always rerun this particular always rerun this particular cell and restore everything. If you right-click on your cell, there is enable scrolling for outputs. You can do that, and that will reduce the number of outputs that you see in that given cell. By default, Jupyter Lab, which is what we're using here, will just not scroll. It will just let that take it however much space. So that's a thing that you might want to do. All right, so this thing, this thing is still unpacking. Let's see. So we'll give it a few more minutes. Now, the next thing that we're going to talk about, I'll just start talking about the next thing. Make sure we're in the correct directory. Now, the way Cactus is distributed, the idea was we didn't want, Paul Walker and John Masseau, when they created this, didn't want to be a silo where, they kept and controlled everything and people had to go through them, right? Because that would not have built the kind of community that they wanted to build. So what they did is we created this Perl script called get components. And the idea is we have this get components reads this thing called a thorn list, and it checks out a bunch of different software repositories from a bunch of different locations. So the Einstein toolkit isn't centralized. It comes from multiple different repositories in different places. Now, if we were building this thing today, I guess we would use Git submodules to do it, and everything would be based on Git. At the time this was built, Git didn't even exist, much less Git submodules. And so what we had instead was sort of a bunch of different popular build systems. There was RCS and Subversion and Mercurial and a couple other weird things around there. And we tried to support them all. So you could have your repository come from any of these kinds of places. And that was, so this is what we built, and it still works. Mine seems to still be running. Has anybody's untar finished? Nobody's untar has finished. Excellent. All right. It's at 97%. There we go. Finished. Done. I just had to wait a few more seconds. All right. So the first step here is we're going to curl the latest get components script, change its permissions so that it runs. And now we're going to tell get components to check out our thorn list. Now, the thorn list that we're going to use is stored under the ET user Einstein-workshop-2024.th. In comments, I have the full checkout for the 2023-11 release. We have a couple of differences in the release that we're using, in the thorn list we're using here from the official release to support the Asterix tutorials later on. When you go to run this, you should see something similar to this. It's going to check out. Why is checking out space-time? Interesting. Okay. All right, so the next thing we're going to do is configure and build our cactus simulation. And what we use for this is a tool called SimFactory. SimFactory is a tool that's written in Python. And one of its primary purposes is to insulate us from the variations of the machine. So where this is most noticeable is when you're compiling, right? You know, trying to get the right balance of which MPI to use, which, you know, which fast Fourier transform to use, which HDF5 library to use, and all this other stuff, which compilation flags do I want, and so on. These can all be somewhat difficult things to work out on a new cluster, and sometimes involve a lot of trial and error. And if you get one, but once you figure out all these details, you can capture them with SimFactory and make them available to others. And we try to keep SimFactory up to date for the major supercomputers that we use. All right, so the first thing you need to do if you're going to use SimFactory is you invoke the setup silent command, where SimFactory does an initial configuration of itself. All right, and it just keeps track of what my email address and who I am, and you know whether I have an allocation or not at the moment. All right, the next thing I'm going to do is build. Now, in this case, the build should do very little. And you notice there is a magic percent slurm. That was something I invented for the purpose of doing these notebooks. So what that will do is it'll throw the build process into the slurm queue and potentially distribute the work away from the web server and onto multiple nodes. And it should result in things just running faster. And it produces a lot of output even when it's doing nothing. That is, the Cactus build system does. It's got a few things it always builds no matter what. And so it's not quite done yet. If you were trying to build the full Cactus system, it would be, you know, as I said, we would all be sitting here until tomorrow because we would overload the disk system and there'd be so much for it to do. It's running slightly slower than I would expect. But as you can imagine, once you take, you know, you can get any system working perfectly for one person, and then you put it into a full classroom, and yeah, it's slower. All right. So any questions on anything so far? All right, so once we get this working, the first thing that we're going to want to do is we're going to run a simple parameter file. And that's going to be, shoot. Oh no, this is fine. This is going to be a part file for hello-world.par, and its contents are listed for you right there. It just says active thorns equal hello world. It's just going to load that one module and run it. And I'm going to click Shift Enter on this and on this next command. So SimFactory, when it runs simulations, it's got two. Yes.
All we've done. It's just there.
Yes, we've downloaded the code and we've compiled it. Right, and then we set up SimFactory, which is the other one thing we did. And let's see how I'm going. Oh, looks like I'm making a lot of progress. Still checking things. Compiling a few random. You know what? Whenever we do this, some random weird thing goes wrong. Why is it doing compilation? The last time I ran this, it didn't. But this time, okay. So strange. Just a few random files here and there. Huh. All right.
All the part about the active thorn
That is the minimal par file, yes. Well, that's what this one has, Roland. Okay, it won't do anything.
No.
Sure, okay, you can have an empty one that does nothing, I guess. All right. But in reality, having an empty one and having one that just says hello world isn't particularly useful. All right, so it's almost done. Formalin is a special thorn. We don't technically need it, and it does waste some resources when it runs in terms of compile time and so on. But what formalin is useful for is when formalin runs, it captures your source code and every detail about your build, so that later on, if you want to find out what you did, right, it's preserved. Because you might have made modifications to the source code in small ways when you compiled it for the machine or for some other purpose and forgotten that you did it. This is not an unusual situation. And formalin helps you preserve everything that you did for the purpose of recreating runs. When I was a grad student, we had some black hole collision that we did, a head-on black hole collision. Back then, the 2D calculation was state of the art. And it got on the cover of Science, and we had this nice visualization of gravitational waves on the cover of Science. A year later, we had no idea how we did that. I mean, so you need tools like formalin to help prevent that sort of situation. Right? Reproducibility of software was something people hadn't really started to think about too hard back then, but we do think about it now. All right, it's still pondering. Ah, look at that. Look at that, it's linking. It's always great when you can get excited about the most basic things. My code is linking. All right, so it's going to finish linking. It's going to run some other, it's going to compile some other small programs, and then it will be done. And then we're going to run the Hello World program. So let me talk about SimFactory a little more. So SimFactory, you see, has, when we invoke it, we have this create, run. So create and run are two distinct steps in SimFactory, right? So I can create a simulation, which, you know, tells it which parameter file I want to use and some other information potentially. And it just creates a placeholder for doing simulations there. And then I can either use run if I want the program to run in the foreground, or submit if I want it to run in the background. In this case, I've compiled, I've done create and run all in one step. But in practice, I might separate them. And the advantage to separating them is that I might want to do run more than one time. So if I do that, it will pick up from a checkpoint file. It potentially can pick up from a checkpoint file and continue the simulation, depending on, you know, whether I've configured things properly for that. Okay, right. So I should be almost done. We will be capturing load metrics on this to see what's going on. We always do. Still linking. Any questions about any of these pieces so far? So one of the things that SimFactory isolates you from, right, in addition to isolating you from the build details that you need to get everything to compile perfectly, is how to run things. In principle, SimFactory should be able to give you the same commands to run your code, whether you're on a laptop with no job manager, or if you're on Slurm or Load Leveler or SunGrid Engine. You know, because each of these machines, or Torque Moab, all these different job management systems work slightly differently, and you might not want to keep track of all the details of each one. Look at that, all done. Building utilities. Now it's got to build the utilities. And then it should run my Hello World program for me. Has anybody gotten Hello World to run yet? Are you behind me? One person? Okay. So we all proceed at slightly different paces, of course, depending on the way the jobs happen to fit into the system. And looks like I'm building all my utilities. Done. And voila, my job runs. And somewhere in here. Here we go. There's a schedule tree and hello world, hello world, hello world, hello. Okay. How many people have gotten to this point? Still just one, two? All right. You're going to get there shortly. Okay, so that's the first Cactus program. That's the most simple step. Any programming language or framework or whatever you want to use, the first thing you need to do is you need to know how to run Hello World. And so we have accomplished that. That's no small thing. It is a small thing, but it's also not a small thing. Okay, so the next thing we want to do is jump right from doing Hello World to running a TOV star. So a TOV star, so I skipped some cells. Yes. No, you're going to specify that elsewhere. That doesn't go in the par file, the number of cores and everything. So I failed to run these two cells, and let me just run them. So I'm going to create and I'm going to submit. Yeah, okay, overwriting. Okay, so I've created and submitted these two things. And now I'm going to list the simulation. So SimFactory is going to show me what's running. And it says that the TOV simulation is active and running as job ID 40. I can now do show output. And it's going to start running and showing me output as it does this TOV simulation. And it's off to the races. So this will now run. This is already well on its way. Now, this particular step, unfortunately, will take 20 minutes. I think what we've said above here is, these are my glasses with the weak frames on them, fall off my nose. Yeah, we set up here that our maximum wall time would be 20 minutes. And we do this because, you know, this code can run for a very long time, especially when the machine is loaded. And 20 minutes is kind of like a balance where we get something substantial and we still are able to talk about other things that are going on. But in principle, you could take this home and you could run it for longer if you so chose. Yes? So it has certain defaults that it assumes, right? And the defaults are going to be specific to the configuration file for the machine. In this case, what I'm saying is I want to run two. So when I say 2 cores and num threads equal 1, that means I'm going to run 2 MPI processes, and each MPI process is going to get 1 thread. If I wanted to run 1 MPI process with 2 threads, I would have said cores equal 2, num threads equal 2. So if you want the number of MPI processes, it's going to be cores divided by number of threads. So that's just basically the way that's basically the way you submit things to SimFactory. Let's check on how it's progressing. Yes. No. It's all experimenting. It's different on every machine. I want to say that a lot of the time you only want a few threads per core, like 2 to 4 or something like that, and then let MPI handle the rest of the parallelism. But this general rule should not be taken as gospel. I mean, you just have to test. Yeah, it depends on the node. Yeah, there's so many details it depends on, and so many of them are just things you can't figure out. You just have to experiment if you really want to know. I mean, how many pneumo domains does the machine have? What is this cache? Blah, 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 blah. So many things. Okay. It's almost infinitely complicated. Anyway, while that's running, what I'd like to do is take a little look at the par file. And I don't know that I want to talk about every single thing that's in here, but just some subsection of things. So active thorns, time and method of lines. So method of lines is going to be our time integration method, right? And if you want to, you can take a look at these par files. Let me do that interactively. So you can open a terminal, right? And you can go into your Cactus directory and repos Einstein, what is it? Utils time? No, Einstein numerical. No, it isn't. It's Mal, Cactus numerical? Yeah, okay. So if you want to look at the Mal par file, right, you can see all the different time integration methods that are available to you. You have iterative Crank-Nicholson and Euler if Euler is what you really want. We have various types of RK2 and RK3 and RK 4.5 and RK 6.5. There's an RK 8. There's a wide variety of things in here. I think that RK4 is what most people use, but I just, there are other possibilities, and you can choose different things if your simulation needs it. So that's what MAL is for, and this is how you find, the various. So I would encourage you to look at the parameter files and the documentation there when you see strange things in a par file. Okay, so that's the first thing. And then we have coord base and cart grid 3D. These are the two things we're going to use to define our grid. So we've got a couple of things that we set here, but the thing to notice is xmin, ymin, zmin, xmax, ymax, zmax, and dx, dy, dz. These, I hope, are fairly intuitive names for how you set up the grid. There's some other stuff, as I say, around here, which you might want to look up. So very few people who run Einstein Toolkit start with an empty par file and just start typing things, right? What you typically do is you borrow a par file and you start editing, because there's so many things that you can potentially set and can potentially need to set. Figuring it out from scratch is just difficult. So TOV star is a nice thing to start with. Because it's a nice, simple problem, as simple as you can get and still be sort of a real problem. And anyway, so that's how you set up your grid. And then you can give carpet instructions on mesh refinement. Now, in this case, what we want to do is we want to set up a mesh refinement box around our TOV star. We're going to only have one level of refinement because we don't want the computation to take forever. This is going to be an under-resolved TOV star. If you want to take this notebook and what you've learned here and beef up the processing and the grid, and the grid size and so on, you can. But what we're going to do is we're going to have one refinement center, and we're going to have two refinement levels. So we'll have a coarse grid and a finer grid, and the radius of the refined grid will be 12. That's the radius of a rectangle, not a sphere. So we also specify the boundary sizes. around the grid. Remember, we talked about ghost zones before, and we have ghost zones, and we have boundary zones. This is the number of boundary zones that we have. Typically, we want that to match the number of ghost zones. There is a shift that we do to the origins. That's just sort of getting the coordinates in a certain way that we want them. Active thorns, reflection, symmetry. So what we're going to do in this case is, we're already doing something silly here, right? We're taking a spherically symmetric problem and we're evolving it in full 3D using adaptive mesh refinement, okay? And obviously it would be much more computationally efficient to evolve it in 1D, but the point of doing it this way is that we can test all our 3D infrastructure and make sure it's not messing things up. So, but even though we're running in full 3D, we're taking advantage of spherical symmetry in that we're creating, we're only evolving one octant. The other 7 pieces of this simulation are just assumed to be identically the same as ours. And so we specify this reflection symmetry to make that clear. So let's see, spatial order 4, ADM macro spatial order 4, we're going to use 4th order differencing. Poisoning is something that you can do for checking, for error checking. It potentially slows your calculation down for a bit. Does somebody have, we have an extra bottle of water. I have this rule that whenever you go to speak in front of a room, you should always have a drink with you. And I did not obey my rule. And now my throat is scratchy. Yeah, would you please? All right. Okay, so poisoning. So poisoning is a NaN, a so-called not a number value, and we introduce these onto grids when they're uninitialized. And this helps us catch problems where we don't initialize things properly. It can also catch things when our numerics go astray. Max refinement levels. So this is the maximum possible number of refinement levels we could pick. And in this case, we've only picked 2 to actually run, but it's got space potentially for 10. And when it does this, each step of the course grid is going to be 2 to the 9th is in terms of internal steps. Ghost size 3, that matches the boundary size, which is what you generally want to do. We also specify a prolongation order in space and time. So when you do adaptive mesh refinement, there are basically 2 choices you can make about how the refinement is done. You can subcycle in time or not subcycle in time. What that means is, if I'm subcycling in time, that means for every step, I take 2 steps on the fine grid for every 1 step I take on the coarse grid. And that creates certain complications, right? When I want to do the synchronization, I now, on the fine grid from the middle, I potentially have to interpolate the data from other time steps. And my rescue is coming. Yes, I have a water bottle.
I figure you're a 2-fisted drinker.
All right, I thought one was for you.
No.
All right. So we need to fill in those boundary zones on the fine grid in between steps of the coarse grid, and that's what we do prolongation for. Any questions? Yes. No. No, you can just sort of put things in any order and jumble them around. In principle, you can set something down here and then use it up here and so on. It's supposed to be order free. Any other questions? By the way, the par file supports a lot of basic math. You can do like multiplication and division and maximum and minimum, and you can, use other parameters to calculate, one parameter to calculate another and so on. I do not believe that it is Turing complete, but it does allow you some basic functionality. Okay, the next thing is time DT fact. So I don't know how many of you are familiar with Courant instability, but this is a problem that you can have, right? For your numerical method, if you take too big a time step for the grid that you have, your code becomes unstable. High frequency noise appears, and in a short period of time, you are left with nothing but nans. Like one grid step is going to be 10 to the 60th, and the next grid cell over will be minus 10 to the 60th, and then it'll be plus 10 to the 59th and minus 10 to the 59th. So every other grid cell, you get a wild swing in value. And what happens is, if you take too big a time step, you get some small difference from one time step to another, and it gets magnified with each time step. And the cure for that is to keep the time step small. There are also, so you saw that list of numerical methods, right? RK4 is stable if you take the right size time step. But if you take, say, Euler method, it's going to be unstable no matter what time step you take. It's just if you take a smaller one, it'll last a little longer, but it's still unstable. And the same is true for RK2. But once you get to the higher order methods, for various reasons, it becomes possible to have them be stable. And in this method, we are using RK4, and you need to give it the right number of intermediate steps and scratch levels. Some of this is black magic, sorry. And then we have our NAND checker, which is going to periodically going to check for NANDs and kill the calculation if it finds them, because once they've appeared there, your solution is no good anyway. EOS Omni and GR Hydro. So this is a neutron star, which means it's using hydrodynamics, and it needs all the different things that go along with that. You have to specify your equation of state, your reconstruction methods, what to do if you've got discontinuities, and so on. In this case, let's see. Then other active thorns, generic FD, NuRad. So NuRad is going to specify an outbound radiative boundary condition. And what that should do is, if I have waves propagating off the grid, they should propagate off the grid. There shouldn't be any reflection. It's a tricky thing to get right, and you can probably never do it perfectly, but it's something you want to strive for. Let's see, how are we doing on our simulation? I'm up to 171520. Anybody beating me? So, all right. So that just takes a while. All right, other parameters for the TOV solver. We need to specify the initial central density, the K and the gamma for the equation of state, and some other hydro parameters. IO outdoor equals $pi par file. So this tells you what the name of the output directory should be that all the output files should go in. And almost always people want it to match the same name as the par file. So in almost every par file that you'll ever see, you'll see this particular line. And maybe it should just become the default and you shouldn't have to put it there. Here's another option that you can specify for IO, and that's the out mode, whether we want one file or one file per process. One file per process is going to be more efficient because it means you don't have to route things through the processor 0. But it's inconvenient in other ways, and we're not going to deal with that complexity here, so we're going to use one file. In this case, there's some screen output. We're going to output every 512. We're going to output some information variables. The maximum of these quantities, physical time and maximum of value of rho. You can do various other kinds of output as well. So all of these things follow a similar pattern. So we can output the scalar variables with a maximum. You can put the fully qualified name with Thorn and variable name. And then in curly brackets, you can put some kind of, whether you want reductions or, what reductions you want, norm 1, norm 2 maximum, and so on, infinity norm, and so on. It depends on what you want and what you need. And you can put out, you can output 1D information. So you can find, say, the value of the rho and the pressure and epsilon and so forth across like the x-axis, the y-axis, diagonal line across all 3 axes, and so on. You can choose for HDF5 output, the binary output instead of the ASCII. You can output buffer points or not. And IO HDF5 2D output is done every 2048 steps. Generally speaking, IO is going to slow you down because not only are you writing to disk, which is slower than your CPU, but you're competing in bandwidth to the disk with everybody else who's on the machine. So you want to make sure that you don't do more output than you need. All right, let's see. That's entirely enough talking about that. Hopefully, I'm getting close to the end of my simulation. Are there questions? Yes, in the back. Okay, so time levels are, I have a value of a quantity now, and I have a snapshot of a quantity one time step in the past, and maybe a snapshot of the time before then. And depending on how I've set things up, I might need those time levels, say, to do interpolation in time. So I think we ask for like a certain order of interpolation in time. We need a certain number of time levels to do that. So there's lots of different reasons why you need multiple time levels for things. But that's one example of them. Yeah, and method of lines sometimes needs them, and so on. Yeah, I suppose it's mathematically true that in principle, all you need from a mathematical standpoint is the initial data and how to get from one step to the other. But the reality is when you try to come up with a numerical scheme to get from one step to the other, sometimes you wind up needing multiple time levels to make that scheme work. I mean, you're right. From a strict mathematical point of view, that's true. But if I tried to, think about this, if I tried to do the Euler method, which is definitely not going to need any past time levels, right? And if I'm not subcycling in time, then I probably don't need it for that either. But Euler is going to be unstable, so it winds out that for reasons of numerics instead of reasons of math, you need these other levels. Yes. Could I repeat the code again? You mean show the power file?
Yeah.
Oh, the vampire. Yeah, it should be in the chat. Withered Vampire 2. It should be in the chat. Yeah, the capital W and a capital V. The Withered Vampire 2. Yeah. Ah, good. It looks like I'm done. I hit time limit. See, I talked for just the right amount of time. How do I do it? All right. And then I list simulations, and it lists them as finished, both finished. If I had wanted to cancel the job, I could have done it with the stop command, but I didn't, and it's commented out anyway. If I wanted to delete everything I did, I could purge it, which I don't want to do because I want to analyze it. This is going to show me the output directory. That's where SimFactory put all my files. That's the naming convention it uses. So it's got, simulations directory where it puts all the simulations. It's got TOVET, which is the name of my simulation, and then output 0000. So potentially I can have more output directories if I restart from checkpoint and continue. We have some code we use to, that's exciting. What the heck? That's just wrong. Let's get rid of the bash thing in the front. So I know that I ran through this notebook multiple times and executed every step. And still something like that can happen. It's just kind of amazing to me. I don't understand how, but anyway. Bash and percent bash and percent pip are not compatible. Okay, so now what we have is we have a function to plot our time series using Quibit, which is the package that comes with the Einstein toolkit for doing graphics. And this is going to, it's going to pull out all our data from the files that we've generated and plot it. So that's what I got for my trouble. And here is a density profile, which you can see my TOV star sitting in the center of my grid there in the 1 octant. Now, this is 2 versions of the code. Sorry, something looks a little unfamiliar to me. All right, so I'm having, so this is the pressure and the cold pressure. And there is a fully symmetric view of my data where I have the reflection symmetry undo is performed. And then I'm finally going to compare. I'm going to compare my simulation with pre-recorded data. So the pre-recorded data, the stored values are in blue, and it shows you how the thing continues. The central density, our results comes from our actual simulation, and it's actually more reliable because the stored values were stored at low precision. And so that shows you how well the central density did against the expected answer. And as you can see, it's almost indistinguishable. And this is a way of turning the data we got into a compressed data format similar to the one that was used to store the values. So that takes us through how to download, compile, and run the Einstein toolkit for a basic TOV star, and to do some rudimentary visualization of the results. And I think I'm way ahead of time, but I'm done. Any questions? What's your error? I can't hear you.
It says that the
factory doesn't exist.
I don't know where it's put that. Mine crashed too. Mine said cancel this time.
No, that's not crashing.
I know.
That's expected.
It didn't. The plotting stuff didn't work out.
Okay, I'd have to look at each of those things.
Mine says some factory Vincent.
Okay, so you need to go back to the top. Something went wrong with your checkout process at the beginning. Well, I don't know. I guess I can come over there and look at particular details, and I can do that in a minute or two if we have no general questions, because we have time. I can try and figure that out. Yes.
In general, when being started on a cluster.
Well, you would start at the top of this file with the instructions it has there. A lot of those files are Mac specific because Mac is the nightmare of this thing. But you just follow the basic instructions for the particular build that you're using, Ubuntu or whatever, and you will run into trouble, right? Because yeah, you know, the Python version is 2.8, or you know, they've got an old MPI or an MPI that isn't linked properly or something like that. There's always, sometimes I think I spend half my life figuring out how to compile things.
I get that.
And that's just life. And you know, what's one of the things SimFactory is trying to do is trying to make you spend a slightly smaller percentage of your life compiling things.
Well, is that where you got gray hair from?
I'm sure it's not, but
I think there was a question in the chat. I don't have to.
can somebody what's the question from the chat? Would you recommend users familiarize themselves with Quibit for reading data into Python for more modifiable plots, or would you recommend reading the ASCII binary files yourself? Generally speaking, we recommend using Quibit, but sometimes it's valuable to just understand the ASCII files at some degree. Just take a look at them once or something like that, because it's, you know, if you're going to drive a car all the time, it might make sense to learn how to change the oil, even if you're going to normally get it done for you. But yeah, generally I would say use Quibit. Any other questions? Anybody online? Okay, I guess that's a wrap. And I can sit with people who are having specific problems if you like. Okay, well, we can take a look at that. I keep expecting to hear recording stopped. Brandon?
You had some questions,
Yeah.